Hi, everybody. I'm Stefan. I'm a second year aerospace engineering PhD student, and I'm part of the Avoid group. So what we're aiming to do at Avoid, it's funded by the EPSLC and Rolls-Royce, is to be able to simulate exactly what happens to Avoid during the curing process of the composite. So specifically, what I've been doing is we currently have an excellent SPH model that can handle resin behavior and gas behavior. And I've been trying to get a model that can handle the behavior of layers of solid fibers. So for example, this ply layer or what have you. So you can imagine to get that up and running, you need a solid model that can handle large deformations, that can handle lots of contact between solid fiber layers, and also interfaces really well with that SPH model. And finally, you need to make sure your process parameters are dead right. If you get all that right, then hopefully you'll have a tool where someone gives you some process parameters and we can run a simulation and tell you the exact sort of void distribution you should expect from your process. So that's the aim. What I'll talk through today is just give you a brief overview of some of the challenges I've had at each stage of that process, and then talk you through what's coming next. So the first stage is creating the solid model to begin with. What we've gone for here is a rod element model. So we model each fiber layer as a set of points connected by rod elements, and then use finite differences to calculate your bending forces and your tensile forces. The first challenge you run into with that, of course, is that we're dealing with really high stiffnesses here. And that can lead to some very small time steps. What we've done to combat that is we're using a linearized implicit form of our force equations. And that means that that's no longer limiting our time steps the way it was. Viscosity is something we also use a linearized implicit form for as well. So that's already in the code, and we were able to slot this in next to it quite nicely. The second problem you run into is obviously contact. Again, SPH is very helpful for this because we're already keeping track of the proximity between all the different particles. So applying a linear repulsion force between two solid particles isn't that difficult, and we've been able to do it. As for those large deflections, well, there's a reason we chose this rod element model. It performs very well, even for large deflections, even for buckling, it remains very accurate. So we're confident it can handle that. The next stage, once you have your solid model, is coupling the solid with the fluid. So if you imagine our line of points here now has to represent a big, thick region like these red lines here, which are a ply layer. And we have to have resin and gas particles traveling through that. So how do we model that interaction? Well, we slow down the resin and we slow down the gas in proportion to the permeability of the fibers. We're able to get a reasonable experimental measurement of that. So it's actually quite a representative way of modeling that interaction. Obviously, some things are impermeable, like a vacuum bag or a boundary. That needs separate code, but we've been able to do that as well. And we also have to bear in mind that if you have a dry region inside a ply layer, there's not going to be as much space for resin in there as in a pure gas bubble. So we take account of that when we set it up. But with that coupling up and running, we then need our initial conditions in our cure. And here we really benefit from the experimental side of the Avoid group. Pedro Hernandez will tell you more about that later on today. But essentially, they've been able to use machine learning to give us some really good measurements of dry areas and voids in prepreg samples. And we were able to scan throughout the cure process. So we get really good data. And we're able to take that, quantify it, and put it straight into our simulation. So you can see these dry areas are taken, the distribution are taken straight from there. And they also the experimental side can give us all the viscosity profiles we need for our process. So in terms of what's next, we need to speed up the solver a bit more, decrease the time step a bit further, and just scale up to larger time test cases, as you'd expect. We're going to add a variable fiber thickness model developed at Bristol by Jonathan Belnu, which should help as well. And finally, we need to define our predictions experimentally. So in terms of how this looks when you put it all together, what I've got here is on the left-hand side is a vacuum bag, on the right-hand side is a boundary. In between is a bunch of resin, and we have some fibers with dry areas sprinkled along them. The left-hand side is not so viscous, the right-hand side is viscous. And if I press play here, hopefully this should give you some idea of what it looks like when we bring this all together. So yeah, that's basically me for today, and I'll look forward to talking to you further in the questions session. Thanks very much.